My guest today is Professor Prem Kumar, who is Professor of Information Technology in the McCormick School of Engineering and Applied Sciences and Professor of Physics and Astronomy in the Weinberg College of Arts and Sciences at Northwestern University. His current research is funded by the National Science Foundation, the Department of Energy, and the Defense Advanced Research Projects Agency. Welcome, Prem.
Thank you.
Yeah, thanks for doing this. So, um, you are a dedicated educator. Uh, since the world is round, you're back the other side of the world, and it's like midnight, past
Right.
midnight over there. Um, so, yeah, thanks for doing this. And so, I got some of your papers. Um, and before we get into it, I know that we're going to talk about quantum entanglement and quantum teleportation. But as I mentioned, I sort of I have a general understanding of these things, but our audience is very eclectic. So I want to start at the basement, so to speak. So, what exactly is quantum entanglement?
Okay, so I guess that's a very good question, and certainly entanglement is a statistical dependency. Again, I'm going to say a few things, and then we can back up
Yeah.
and go into the basics. So in real life, we have random systems, right? Things that are random, and classically speaking, if I toss a coin, there's a probability of it being head or tail. If I have a fair coin, it's 50% heads and 50% tail. And if I roll a dice, and the numbers change, but the idea is the same. And if I take two coins, and each one is independently, statistical, but I can imagine a situation in which there's a correlation between the two. If I roll a set of dice, then if somehow there is some interaction between them, one shows up as a one, the other one shows up as a one, and one can construe things in which things are statistically dependent on each other, right? And that would happen if I tie up the two coins so that when they roll, they kind of each one rolls the same.
Yeah.
In quantum mechanics, we have randomness also, but quantum systems are random in more deeper ways. So, for example, you could have statistical correlations, but a priori, you could not assign a classical manifestation of those. So, for example, you could have two atoms being simultaneously behaving the same way, but a priori you couldn't say. Each one is random, but when you roll them, if one comes up heads, the other one also comes up tails, and you couldn't predict them a priori. So, so those kind of notions are often called entanglement. So this is the quantum meaning that things are random in a deeper way, that they are entangled. So they cannot be described statistically by a classically random process. And oftentimes, people say that the system violates Bell's inequalities. I mean, this is John Bell, who was a scientist. He quantified the notion of classicality of a system by assigning a certain characteristics to quantum systems. If you make measurements, all classically correlated systems that have physical reality of the kind that I described, that you roll a dice or as flip coins, then they follow certain inequalities that always fall, for example, less than 2, just as a metric in that case. But quantum systems, they can have values greater than 2. So 2 square root 2 being in that particular case of Bell's inequality. So if you do experiments and you find that this number turns out to be between 2 and square root 2, 2.8 something versus 2, then that system doesn't have the so-called local realism of the kind Einstein had imagined, right? So one has these quantum systems that behave in a way that's more than what classical description of reality would seem to imply.
Okay,
So
so
that's what we mean by entanglement in some ways.
entanglement, yeah. So if I understand this correctly, Prem, so Professor Morden from NYU
Mhm.
was on the podcast, and recent Nobel Prize for Bell inequality related things. I can't remember the names of those folks, but it seems like we have. Oh, maybe. Let me make a statement. You can object to it. Have we proven that it is really quantum mechanics that drives things? So, as you say, the classical statistical expectations
Mhm.
of two particles far
Mhm.
apart
Mhm.
cannot be satisfied by the observations that we can make on them, right? It is a lot higher than the correlations
Right.
what statistical, yeah.
Right. So I think the experiments seem to imply that the local realism of the kind that Einstein had imagined does not hold. I think that's so. Einstein had a picture of reality in his mind
Mm,
that that all properties of particles are local. That's why it's
yeah.
often called local realism. And all we're saying that quantum mechanics has these non-local features,
Mm.
and to me, after having worked in these areas for a long period of time, it is a mystery. I mean, of course, to
It's
quote Feynman,
counterintuitive.
it is
Counterintuitive.
very counterintuitive. So,
Yeah.
so to quote Feynman, no one really understands how quantum mechanics
Yes.
works
Yeah, yeah.
intuitively, but that's how it works. We know how it works, and we can compute from it. And everyone has their own way of understanding. Everybody intuitively rationalizes things. And the way I do it is that it's just that the quantum systems, extended quantum systems. So in the example that you mentioned, where let's say I have two particles that are entangled,
Yeah.
no matter how far apart their joint wave function. So when they are entangled, they are in this one unique state. Okay, so they are actually one thing, which expands into a physical universe
Yeah.
where the wave function spreads out over whatever the dimension of the universe is, but then they remain intricately linked.
Mm.
But there's still one entity, and if you measure piece of it in far corner of the universe, the other piece of it elsewhere is affected when that measurement occurs. Right. So
Yeah. So I don't know if we talk about wave function that much, but yeah, the wave function is also a fundamental thing to define, right? So we have this particle wave duality,
yes.
and so if I understand this, very peripherally, is that you take two photons, so I said two fundamental particles,
Mhm.
entangle them.
Yep.
Now they are sharing a wave function
That's correct.
that is, so the distance between them doesn't matter anymore. It is, in some sense, it's the same particle. Is that the way to think about it?
I would say it's the same two particle state. Okay, it's the wave function of two particles. It is the
Yep.
wave function which has two units of matter in it, two units of energy in it, two units of whatever it is. So when we observe them uh, through some interaction with an apparatus that's measuring those things, then there are two clicks, two observations. The events occur, there are two events that occur, but
Hmm.
it's the same underlying wave function. So I think that's what gives it this new notion, counterintuitive notion of oneness yet being two things,
Hmm.
right? So
Yeah, I mean, for 300,000 years, Homo sapiens grew up looking at objects They were all separate. I mean, object X is definitely different from object Y. And then last 100 years, we were given a notion that that may not be quite true. They share some sort of universal wave function,
Yep.
and their properties are determined by that, right? So, I mean, there's a good reason why it's counterintuitive for humans.
Oh, absolutely. I think we all strive to have this underlying reality, whatever. I think different cultures, let me just say it that way, because how we intuitively understand our surroundings in some ways also is very cultural dependent, right?
Yeah, yeah,
So if you grow up in a certain let's say in India, I mean, as you're
yeah,
growing up, you're given a model of the universe, so to speak, if I were to use that language. If
right.
you grow up in Western culture, but scientific method is a very different thing, right?
Mm,
So we ask, we observe, we rationalize, we build a model, or let me call it model. It could become a theory, right?
yeah,
Because up until it's tested, it is still a model, right? So
yeah,
at some point, you keep on testing, and a uniform picture appears. And a complete picture may never appear, right? Because
mm,
the more you investigate, the more intricate things you find.
yeah.
So right now, for me, a lot of people start going, the moment you start talking about entanglement, they start thinking about parallel universes. And, I think it's, I mean, the more you probe, the more you investigate, the more questions arise.
Yeah.
And I am not sure if humankind has the ultimate understanding of how our universe works.
Yeah, so Prem, that'll be the ultimate irony. I'm fond of saying God has a sense of humor. She sort of directs you in some directions, and then as soon as you think that you found something out, she drops you to start all over again. I mean, this is a human life, really. I mean, I don't think we have figured anything out. So I want to go into your paper, but I just want you to react to it. Yeah.
Yeah, so I think different, I mean, you have the way you have stated is one way of thinking about it. I think different people think differently. I mean, I think in ways of, to me, God is the universe, right?
Mm,
So have we understood the reality? To me, God is the laws of nature, right?
yeah.
So, in some ways, have we understood everything? Perhaps not. And yeah, I mean, humankind over the course of, it's very easy to personify things, right?
Yeah.
But in the end, we all believe that there is an underlying something, some force in the universe of which we are part of, right?
Right.
And as humans, we get this tendency of asking the questions, what is it? We're very curious, we're very inquisitive in
Yes.
some ways.
And there's so much information. So, this is what makes it more difficult. So I want to go into your one of your earlier papers,
Mhm.
designing noise robust quantum networks coexisting in the classical fiber infrastructure.
Yep.
So you say here the scalability of quantum networking will benefit from quantum and classical communications coexisting in shared fibers, the main challenge being spontaneous Raman scattering noise. So, I mean, this little bit of a departure, isn't it? I mean, we've been thinking about quantum computers and classical computers and networking and communication as sort of a recent phenomenon. Um, but you're saying here that we could sort of combine them to make it
Right,
more efficient.
exactly. Right.
Yeah.
Yeah, so I think that's a good segue of getting into what is motivating me in current research, and
Yeah.
in some ways, a lot of the community in the quantum area. And people talk about, quantum 2.0 technologies, for example. How do we harness these quantum principles of what I often describe as superposition, measurement, and entanglement. I mean, those are the key characteristics that come into play. Superposition, which is, the linearity of systems, is a very common thing, which is obeyed by almost all systems that we know. Even classical waves, you add them, they reinforce. You add them out of phase, they destructively interfere. Water waves have them. All kinds of classical systems have them. But when we get into this quantum domain, when the notion of measurement comes into play,
Yeah.
As we were discussing before, how you construct a measurement, the system response may be different. In some ways, we have this wave-particle duality, and the measurement is, how I look at the system, how I look at that wave-particle oneness in some ways. But then you also have this notion of entanglement, where there are two things behaving as one, or three things, or maybe n things behaving as one. So quantum mechanically, there are lots and lots of degrees of freedom, 2 to the n degrees of freedom, but the whole thing behaves in some ways as a one single unit of quantum behavior. So people have shown, particularly Feynman himself in the late 70s, early 80s, wanted to simulate quantum electrodynamics on classical computers. And one realizes that in order to simulate quantum mechanically even a small system, because the Hilbert space becomes very, very large, it's an exponentially harder and harder system to simulate as the system, an atom goes to a molecule, even a few degrees of freedom of whatever system you have come into play. And so his idea was that if we can make simulating systems, that is computers, out of quantum pieces, then this scaling problem becomes manageable. That if the computers were built obeying the laws of quantum mechanics, then one could simulate a quantum system on another simulated on another system which is quantum mechanical, and then the scaling problem becomes manageable.
Yeah.
And of course, that led to a whole new field of research. People asking the question, can we build quantum computers so that we can simulate more complex quantum systems on a prototypical system that we could control?
Right.
And then came along in 1994, Peter Shor, who introduced this Shor factoring algorithm. All of a sudden, the community, and I mean business community now, because in the early 90s, the advent of the World Wide Web, the advent of networking among the computers, the notion of electronic commerce was taking hold. And President Clinton, in his first term, introduced this legislation which gave the electronic commerce the same power of law that existed for ordinary, paper-based commerce, signatures and commitments and things like that. And all of those were being secured by classical cryptography, which is based on what's often in mathematics called one-way functions, things that are hard to compute one way and very easy to compute the other way. So, for example, take two large numbers, it's easy to multiply them, but if you know the composite number, it's hard to tell what factors that number has. So based on this, e-commerce was taking hold. But then came Shor's factoring algorithm. It said, okay, if you give me a new technology, that is a quantum computer, then I can factor those large numbers in a very efficient way. And all of a sudden, something that was growing, that was scientifically developing as a quantum hardware for understanding basic physical systems, turned out to have a very strong public utility, because if somebody could build a quantum computer and factorize large numbers very efficiently, that
Mm.
becomes a very huge threat to the e-commerce that was just taking hold.
For
Right?
cryptography, right? For cryptography in
For
general.
breaking RSA, which is the algorithm that is being used for key exchange, for example. So all of a sudden, this notion of a scientific instrument took on a very different meaning, and people, governments everywhere diverted research from developing quantum computing as a scientific use case into a very practical use case of security.
Yeah.
So for a long time, research in quantum computing went into trying to build bigger and bigger systems, and people realized that building quantum computers is hard. And it's not easy to tame this so-called, large, giant quantum system, which has many, many intricate parts to it.
Yeah.
Not only control it, but steer it in a way that leads you to this output. That is, when you measure it, it gives you the answer, the prime factors of whatever numbers you want to factorize, right?
Yeah, it is also a scaling problem, right? So I think
Exactly.
yeah, yeah.
So,
So
so,
the number
so
of qubits, I think what IBM and Google have accomplished, I think it's around 100, I think,
yeah,
right?
it's
Yeah.
current technology is on the order of 100.
Yeah.
So that comes to the point that I wanted to get to, is that after a lot of research, almost 30 years of developing quantum computers, people are realizing that it is difficult to scale an individual system
Yeah.
to a large enough scale that you can solve some of these hard problems. Along the way, of course, people have discovered other problems that quantum
Yeah.
computers could be useful for.
Yeah.
So almost everyone these days thinks that to scale quantum computing, one would have to modularize, build the systems at a scale that you can do very well, and then interconnect them in some ways.
And they
And in
can
some sense, that's
communicate.
not different. That's
Yeah.
not different than how we do things classically, right?
Yeah. Yeah. But yeah. So I think the Sun microcomputer CEO that said the network is the computer.
Yes.
And then we sort of went away from it. Coming back to it, a
Yes,
quantum
exactly.
computer is really a network. It's not 100 qubits sitting on a chip that's going to going to fail in a lot
Right.
of situations, right? So that's architecture difference. Yeah.
Right. So almost no matter which platform you look at. In fact, just a couple of days ago, I was listening to Jensen Huang, at the GTC conference. He brought on the CEOs of all 15 or so quantum computing companies,
Mm.
including Microsoft and including Google, and people who are trying to build quantum computers. And it was very interesting to hear that conversation.
Hmm.
What the notion of computing after 50 years of development, right? Which is, the NVIDIA, and, which is the ultimate of classical computing today, or the data centers, the use cases of the classical quantum computing. It took, 60 years to get there, right?
Mm.
And so quantum computing, in that sense, in its infancy. And just like how it happened in classical systems, the everyone's realizing that we will build quantum systems at a small enough scale that, of course, those will keep on getting bigger and bigger. But if we can figure out how to interconnect them,
Mm.
then the larger system, by interconnecting them, would grow at a reasonable cost, because then we will
Yeah.
learn how to scale things properly. So that's the current thinking, and that's where networking comes into play.
Network goes. So so I want to talk a little bit about engineering. I mean,
Mhm.
you at Northwestern and your colleagues accomplished some major engineering discontinuity, let me call it that way. And so I want to understand that to some extent. So you have a paper out very recently, quantum teleportation coexisting with classical communications in optical fiber. So you say here the ability for quantum and conventional networks to operate in the same optical fibers would aid the development of quantum network technology on a large scale. Quantum teleportation is a fundamental operation in quantum networking, but has yet to be demonstrated in fibers populated with high power conventional optical signals. Yeah, so that makes intuitive sense. So talk a little bit about, so let's just define quantum teleportation first. And
Okay,
then I want
sure.
to talk a little bit about your experiment in Evanston and Chicago. Yeah.
Right. Yeah. So teleportation is a quintessential connection between two quantum nodes. So you can think of it as a wiring between the two sides. So let me step back and give you as an example.
Yeah.
So let's say there are uh, two communicating parties, and oftentimes we will call them Alice and Bob, and they are a certain distance apart, right? That's
Yeah.
the lingo that people use. Let's say Alice has a quantum state. This quantum state could be embodied in a photon, a particle of light. It could be
Is that a
embodied
binary?
in.
Is that a binary state, Prem, or is there more to it?
So a quantum state could be, normally we call it a qubit, which is a binary state in the sense that it has two eigenstates. So there's the basis states are two, but the quantum state could be any superposition.
Okay.
So in principle, you can encode an infinite number because superposition will be two real numbers in some way, or I mean, it's a
Okay.
point on a Poincare sphere.
Yeah.
So um, so you can, so imagine you have a quantum state encoded in a particle of light or an atom, two states of an atom, or any quantum two-state quantum system. Then you can transmit that state from place A to place B, from Alice to Bob, by
Mm.
carrying that atom very delicately from one side to the other, or light likes to travel at the speed of light. If it's a particle of light, then it would, at the speed of light, go from one place to the other.
Yeah.
So long as that particle gets from place A to place B, we call that the direct transport of quantum information. That is, that particle carrying a quantum state goes from place A to place B.
And
Now,
that is pretty easy to do, to
um,
transport.
if the distances are small, of course, it's no different than a classical state in a microchip going from one end of the circuit to the other.
Yeah.
So depending on the distances, that may be the thing to do. And coming back to communication, people talk about
Mm.
communication between two ends of a chip, from board to board, from one room to the other, or across the globe. Right. So today, we're talking, far corners of the earth. I mean, you're somewhere in the U.S. and I'm in India. So we're talking, it feels very real time because the information, we've perfected the system so well
Yeah.
that we can send these classical bits of information securely and reliably over very long distances. Uh, but can we do that with quantum particles, quantum states?
Mm.
The current status of technology is no. But
Yeah.
is it ruled out by the laws of physics? The answer is no. So at this point, uh, one way to extend the distance is through the notion of teleportation.
Yeah.
And so in teleportation, back in 1993, Bennett and at IBM and co-workers came up with this protocol, which is called the teleportation protocol. What that says is that if the two communicating parties have a new resource of entanglement,
Yeah.
and they can hold on to that resource. That is, they can store this entanglement into some quantum systems that they can recall that entanglement on demand whenever they need it.
Mm.
So the quantum teleportation protocol works in the following way. It can transfer, the end result is it can transfer the quantum state from Alice to Bob without having a simultaneous quantum direct transmission from Alice to Bob. So what they do is they prepare this entanglement, that is, they share entanglement a priori, they store it, and when Alice wants to transport or teleport the quantum state of a particle she has in her possession to Bob, what she does is she makes what we call a joint measurement on the particle that she wants to teleport and one half of the entangled piece she has. She makes a joint measurement, which is a two-particle measurement, or two, whether they're two photon or two, atoms or whatever that two-state systems she has. She makes a joint measurement. There are four possible outcomes. That is, each particle can be in upper or lower states. So, of the four possible choices, which is can be characterized as 2 bits of classical information, when she sends that information in a secure way, classically secure way, to Bob, that is 2 bits of classical information are transmitted to Bob, Bob can use that information to act on the other half of the entangled piece he has that he priorly shared with Alice. And he can arrange things in a way that the output of that, conditioned on the knowledge of those 2 classical bits of information, is a quantum state that is exactly the same as Alice had.
So let me try to understand this, Prem. My head is spinning. So you got Alice and Bob.
Yes.
And they have an entangled state between them.
Yep.
And the goal of the experiment is to quantum transport Bob's information to Alice, let's say, if that's the goal. Then you need another particle, right? A particle C, Carly. I don't know if physicists use this term.
Yeah, Charlie.
Charlie. Okay.
Yeah, Charlie is. So that depends on how the system is set up. So normally, Charlie is where the measurement takes place, and that measurement could be at Alice's. The way I described it, Alice is the one. She has this quantum information she wants to teleport or send that information to Bob. Without sending that particle she has. Right. So without physically taking and carrying that particle to Bob, she wants to be able to send some classical information that allows Bob to take the particle he has priorly shared in an entangled state with Alice to turn that particle into the quantum state that Alice wants to send.
So Bob can recreate the quantum state of Alice. That is the...
That's correct. Yeah. So because they have pre-shared this magic of entanglement, if I were to say that, it feels like it's magic of entanglement.
Yes.
But upon receiving the classical information of that Bell state measurement or 2-particle joint measurement that Alice had made, that is enough information for Bob to turn this other half of the entangled piece that he has. He may have to set things up in the following way, that if of those 4 pieces of information, that is 2 bits of information coming, if it is 0, 0, I do this. If it's 0, 1, I do this. If it's 1, 0, I do this. And if it's 1, 1, I do this. So, but all that can be set up so that whatever information coming in, the output, whatever 2 bulbs, they either light up or don't light up. But that would be if he verifies that the state that he received is the exact state. And sometimes, we call Charlie is the verifier, or that's. But the point is that once Bob has that classical information, he's able to convert his qubit into a state, and which is if we which is a deterministic process now, because
Yeah.
if he gets the information, he knows exactly what to do.
Yeah.
That state is exactly the state that Alice had.
Alice has.
In the process of making the measurement, the state no longer, Alice is not in the possession. She has destroyed those particles because she's sort of made measurements and they collapsed. The wave function that Alice had is collapsed.
So entanglement breaks at that point, so to speak.
At that point, one EBIT, so we call one pair of entanglement, has been consumed. That's the way I think about it. That this process of teleportation requires a new resource, a resource of entanglement. To teleport one qubit, I had to consume one EBIT of entanglement. One pair of entangled bits have to be consumed.
So Einstein still wins in some ways because you still need some sort of communication between A and
Yes,
B,
actually,
right?
quite right. I think that the Einstein wins in the sense that causality still holds. Often, this is a myth now. I should emphasize here. A lot of times, as you know, I mean, I took leave for 4 years. I was a program manager at DARPA, and I would oftentimes get these people coming to me saying, "Oh, we can do superluminal communications, right? So we
Yes.
can communicate faster than the speed of light." And that actually is not the case. So it is true that if I take two entangled particles and their wave function, as we discussed earlier, it's a one wave function. If it spreads out, let's say these two particles are light particles and they travel at the speed of light, and within seconds they are over far apart. They could be miles and thousands of miles apart, but it's still one entangled state.
Yeah.
If I measure one particle, the other particle state changes. So that effect is instantaneous. And maybe Einstein might have been bothered by that, but I don't think
Yes.
that's so. He was bothered by the notion of breaking local realism. I think what didn't make sense to him, but how can a particle so far away be affected in some ways? And actually, it is not affected in the sense of signaling, in the sense of communication.
Yeah.
You need to receive those 2 bits of classical information, which are going to come at the speed of light, to make any action. So for the collapse of the entanglement, so to speak, which is instantaneous, for it to be actionable, we need to wait. We're bounded by the speed of light. So you really cannot communicate.
Yeah. So I think I'm going to become a religious person for him. This all sounds like it's set up. It's set up for Homo sapiens to chase their tail for a long time and not get to where they think they're going to get to. Yeah.
I mean, I think it is true. We are all trying to understand what reality is, and in our lifetimes we make some progress, and maybe we'll never get there, right? So it's
So I want to
to
understand
me
the
the comforting
engineering.
feeling is that I'm trying, and I'm happy trying. I'm
Either
not
way.
disappointed if I don't understand it.
No. So I want to understand the experiment a little bit more. So this is an experiment that you and your colleagues set up between Evanston and Chicago. That's about 30 kilometers.
It's about 25 kilometers one way, so
45
the round trip.
kilometers.
So okay, this experiment, there are two different experiments there.
Yeah.
So one was the one you were talking earlier. That was on the Chicago, Evanston-Chicago loop. But this teleportation one, we haven't quite done on that loop. So it is in the lab. It's 30 kilometers of fiber. So yeah, two pieces, 15 kilometers each.
30 kilometers. And so we haven't done it yet. It is in process.
No, the experiment has been done.
Okay.
So the 30-kilometer experiment that we published has been done.
Okay.
It hasn't been extended over that 50-kilometer embedded fiber that takes that experiment out into the field.
So the 30-kilometer experiment was also on existing fiber or something different?
So those were two 15-kilometer spools of fiber in the lab, but they had on them same communications traffic that the field fiber would have. So the way we did the experiment was that, okay, let me back up why doing that 50-kilometer experiment is harder. So we needed to generate 2 pairs of photons in a deterministic way. And the way photon generation things works is that we can produce a certain number of photons per second. And 50 kilometers of fiber has enough loss. So 50 kilometers would be in our system at the O band. There's about 10 dB of loss one way.
Oh, wow. Okay.
So that means that if I send a photon, there's 1% chance that it comes back. So that makes the experiment much harder to do.
Yeah.
For the 30-kilometer fiber in the lab, we had enough detection rate that we could make meaningful assessments of the teleportation protocol. So, but in order to show that the teleportation process can coexist with classical communications traffic of the kind that exists on the internet, we worked with a company who provides equipment at the Starlight Communications facility in Chicago, which is a hub for scientific data transport. So all the high-end data that's generated at CERN or high-end data generated by the telescopes in Chile, they all come together and then are directed to various places, to university professors, to national labs for analysis. So there is this facility called Starlight, which happens to be on the Chicago campus of Northwestern University, where they have equipment that produces very high-speed traffic of the kind that's used on the internet. And they work with us to send that light wave communication over that link, that Chicago Evanston link, to us, which we co-propagated with the entanglement distribution / teleportation system over 30 kilometers. And then showed that the teleportation worked whether that internet traffic was on the fiber or not.
I mean, that's a hugely important thing, right? So if you were to make it practical, and we get over the distance constraints, experiments, and you really want to make a quantum internet, and you don't have to build something completely from scratch, that would be hugely beneficial, right?
Yeah, it is. So in fact, coming back to the original motivation, and that's, you started out by asking that question, the quantum computing to scale, we need to build it in a modular way. And so we need to figure out how to interconnect various quantum hardware, whether they are computing processors, memory locations, or some use case, whatever protocol needs to be run. So let's imagine that there are a number of enterprises that want to exchange quantum data amongst each other, or maybe they have quantum data and they do want to compute some joint function on them. Maybe medical records are encoded on that quantum data, and they want to do some global measurements of not revealing whose data it is, but they want to process that jointly in some way. So then that those different quantum entities need to communicate with each other in a networks kind of a scenario. And if the main point that we're trying to make here is that if you were to set up a network a priori from scratch by laying new types of fibers, then that is going to be a very expensive proposition, right? Because laying fiber is very costly, and no user owns their own fiber. There are companies that provides the fiber infrastructure and they lease it. Most people lease them, right? But imagine if I am that fiber lease provider, that is, my job is to lay the fiber and then charge customer a fare for use of it, then my cost that I will charge you is going to be the same whether you send trickle of photons to entangled particles or
Yes.
send trillions of photons with tens of terabits of data, right?
Yeah.
The cost is going to be the same. But
So
tens of terabits of data is a big revenue provider versus trickle of photons, right?
yeah, so I don't know if conceptually I'm thinking about it correctly, Prem. So what you have done is to show that so the quantum computer investments by very large companies, we got up to 100 sort of qubits. What you have done is in some ways to say that is the wrong architecture in the sense that what you need is a distributed quantum qubit network. Then you don't have to worry about things going bad in one node. And just like the internet, maybe there's some sort of a safety mechanism that something can step in when things are going bad, or maybe you can predict it. I'm just making all these things up. I have no clue about
Right,
any of
right. Yeah, I think this is a subtle problem. All of those things are true, but we're not there yet. I mean, so I don't want to imply here that all of a sudden just if you learn to network, then the scaling problem will go away.
Yeah.
It is very difficult. Yes, we've taken some baby steps in that direction. But to get to that truly networkable quantum systems, we still have long ways to go. First of all, the analogy I think it's easier to understand it if we step back and ask, how the development in classical computing, classical networking took
Yeah.
place. As we agreed that, it took 60, 70 years to get to how we communicate now. But back in the 1960s and early 70s, when the so-called internet evangelists, Bob Kahn and Vint Cerf, they did not have in mind of the connectivity we are enjoying today. They were asking very simple question. I have these computing nodes, small scale computing nodes. What would happen, if I can somehow interconnect them together? I mean, they had a certain vision of a network computers. They wanted to exchange messages. They wanted to send emails, file
Yes.
transfer from one to the other, right?
Yeah.
Today, 2-year-old takes email for granted, right? So I think at the time they invented things like TCP/IP, the protocols, without really having the devices to put them into action. So there was a lot of churn that occurred between architecting a network, writing down the protocols, abstracting out, how the users might use, what kind of services could be run on them. And that led to device developments. They recognize what is more important. Is device A more important than device B to set up the network? And that created a churn. And I think the
Yeah.
same churn would happen with quantum devices, and eventually we will arrive at some kind of a quantum network.
Yes, it's almost
And
like
maybe very
saying
different than classical network.
it's different. It's very different. A lot of challenges remain, but it's
Yes.
almost like the quantum network is the quantum computer. Just to play on the words.
It may turn out to be that way, that the network is the quantum computer, just like network is the classical computer, right? I mean, today, I think in hindsight, we have our notion of scalability has advanced so much far along, right? In the, you and I don't want to age ourselves, but, in the 50s and 60s when we were growing up, I mean,
Yeah.
the notion of a network was very, very different. Who could have
Yeah.
imagined? Okay, and let me actually give you a historical perspective,
Yes.
personal historical perspective on this. My kids were growing up in the 90s, and Harry Potter, right? We all know,
That guy
love
knew
those
magic,
books,
I think.
right? And so in 1996, the third book, I think, The Prisoner of Azkaban came out, which had Harry having this Marauders map. right?
Yes.
And the movie came out in 98, I think.
Yeah, my
And
daughter's a huge fan of Harry
so is
Potter.
my daughter as well at the time, right? So the Marauders map back in the mid 90s when the books were being written and the movie came out in the late 90s was a magical thing.
Yeah.
Today, for the last decade, all of us have a Marauders map in our pockets. You have the mapping software, whether it's Google or Apple or whatever, and you can track your friends, right?
Yeah.
So things that were magical
Yeah.
20 years ago, are reality today. So in that sense, the applications like, that the Uber hailing ride, sharing, houses for, I mean, the kind of applications we're running on a very networked system
Yeah.
is very different. And
Yeah.
it's hard to imagine what kind of applications we would run on networked quantum systems. I suspect that a lot of things would occur, a lot of applications of security would be handled that way. People would
Mm.
be able to compute on quantum data in a secure way that the data center does not know what quantum computation is being done, and the users can't cheat the data service provider by saying, okay, we
Yeah.
didn't compute that, but yet that we only pay for this service.
Let me ask you this, Prem. So I don't know if I'm thinking about this correctly. So when internet came along in the 90s, if you can envision what it could do, you could think about applications, how it would evolve, and all of that. The quantum network is a little different, isn't it? I mean, we don't even know, in my view, how one would take advantage of it. I understand the cryptography part of it. That is very clear. But the other things on it, it still remains to be defined, I think, right?
Yes, I think in some sense it's no different than, as we discussed. Could we have imagined the kind of applications,
Yeah.
network ready application we would run? I think I mean, we took the example of this Marauders map, but think back into the 1930s when the basic notions of computers were being written down. The science of computer science was all worked out by Turing and Church and Alonso. So von Neumann, all the basic science of computing, foundations of computer science was worked
Mm.
out in the 1930s and 40s. Because those people had the intrinsic notion of what computing meant, people had mechanical computers for hundreds of years before that, right?
Yeah.
So they figured out what computing means. What does it mean to compute? And along the way, the invention of the transistor, the integrated circuit, it's accelerated the pace.
Mm.
And now we enjoy the fruits of that labor in some ways, the applications we run. But could Turing, could Church, could von Neumann have imagined these shared ride-hailing services that
Mm.
we use today? No. So it's very
Yeah.
hard for us to say, how a quantum network would be used.
We
But I
cannot
can
predict. Yeah.
imagine some, right? So processing shared data in a secure way. I mean, yes, there are classical ways of doing it. There are zero knowledge proofs, and you can compute in a blind computing. There are all kinds of notions that exist in classical computing, which
Yeah.
allows one to do shared processing of data while keeping the data tied to individual users, but process some joint property without revealing what the underlying data structure
So let
is.
me finish up with this, Prem. So I've been an advocate of education stepping forward. I don't quite understand why we have Newtonian physics being taught in universities, because we can program computers to do all that stuff pretty easily. So are we fast reaching a point, I mean, from a sort of Northwestern perspective, that, physics 101, physics 102 should not be starting at Newtonian mechanics. Nobody has any value for it. Let me make a grand statement. Do you think that way?
I think our education definitely system has to change. So two things, 2 points I would like to make here. One is, putting my professor's hat on now. I teach linear algebra, freshman. So every fall, as the new student class comes in, I and a few others in electrical engineering, we teach linear algebra.
Yeah.
And it used to be that at college level, students would start taking calculus first. And, we teach calculus also. And calculus is taught in high schools for centuries now. I'm beginning to believe that we should be teaching linear algebra at high school first.
Yeah.
Because the way the uses of linear algebra are, in systems, in AI systems, as well as in computing, so quantum computing, it's all linear algebra in some ways, right?
Yeah. Right.
And not to say that calculus is not important. It's just that the linear algebra has underlying basis of infinite dimensional spaces, or high dimensional spaces. That's a notion that's much more fundamental in terms of applications that we have today.
Right.
So that's the one point. I wish we will change our curriculum so that linear algebra is emphasized more over calculus. And not that calculus is not important, but it can wait at the college level. Second, I would like to introduce a curriculum in what I would call quantum engineering.
Yes.
So where at a very high level, I think of quantum engineering as a discipline in which students are taught three basic, which are fundamental disciplines in some ways, together with an application area. So, for example, computer science, quantum physics, electrical engineering from the photonics perspective, that is electromagnetism, focusing on the light aspects of it. And then an application space that could be material science, that could be optimization, that could be chemistry. But putting all those things together into one curriculum at the undergraduate level is what if I were to change the curriculum to bring people into the 21st century of the quantum domains of application space, these are the kind of quantum engineers I would like to produce. I think it is a discipline. It's sort of a combination of disciplines that would be very, very important to produce quantum engineers.
Yeah, I like that quite a bit. So, I was thinking, so if we change it, so a physics student never really does Newtonian mechanics or even general theory of relativity. The first course is in quantum mechanics. This counterintuitive feelings that we have is because of our classical training, I would argue. Maybe
I
that,
would
maybe,
I would tend to agree with that, actually. Yeah. So let me give you a perspective in electrical engineering, like, for example, which is a discipline that's been taught in physics as well as in electrical engineering for hundreds of years now. A lot of times, if you look at the curriculum, it is very pedagogical in the sense that you will learn electrostatics, electromagnetics, and then you go to electromagnetic waves. Many institutions have evolved now. They teach electromagnetic waves first, transmission lines first, and they make analogy to antenna systems or fiber optic systems because they connect with applications.
yeah,
Whereas not that electrostatics is not important, but there are very few people who are very much interested in how copiers work, for example, how static electricity use is done, but
yeah,
much more so than the cell phones that we use or the radio transmissions we have. So by the same token, I think we need to revise our curriculum in a way that we see the application space, the connection with the applications, and then we connect them to the basic sciences.
Looking
So in
forward,
this,
applications, future applications, you mean, right?
exactly right. So
Yeah.
I don't mean to shortchange the basic training, right? So in my mind, a 4-year degree program in quantum engineering would be something like you take your basic courses freshman and sophomore year. It's only in the junior senior year when you
Mhm.
are taking major specific courses.
Yeah.
This would be an interdisciplinary major, which brings together physics, computer science, and electrical engineering in an essential way, feeding into a domain pool, whether that's material science or whether that's optimization or whether that's chemistry. It could be policy, it could be law, it could be anything else for that matter also.
Yeah, I mean, Northwestern, as you know, is in a really nice position because at the end of the day, a lot of this practical experiments requires material sciences innovation.
Oh, absolutely.
Um,
Yes.
and so I hope, I hope Northwestern heads in that direction. Yeah, I'm quite unsatisfied, dissatisfied, I should say, with physics education. I mean, if you're spending 6 years learning all the stuff that has no utility in the future, that's 6 years wasted in many ways. So,
Well,
um,
my physics colleagues probably will disagree, but I think in some ways the point you're making is that we need to make our educational system more relevant.
yeah,
And in some ways, I think, you're at Duke University, and I'm sure I have colleagues there, and we all strive to do two things as we teach our undergraduates. One is to make them job ready.
yeah,
Second is to make them lifelong learners. That is, instill enough basic knowledge in them so that as the winds of technology change, they can continue to adapt, while at the same time they have enough skills in their junior, senior years, and they
to
graduate
survive,
that
to
there's an
survive.
employer out there willing to hire them.
Yeah,
So I think we need to make our curriculum has to evolve.
yeah.
Uh, so
Excellent.
that's
I
the
know
way
it's
I think about it. Yeah.
yeah, it's very late for you, Frame. So yeah, thanks so much for doing this. I mean, it's an incredibly late time for you.
It's
So
the hour has gone by, and it's been a lovely conversation, and I feel much more awake now than I was at the beginning.
go to sleep. Thanks so much.
Okay,
Thanks
thanks,
again.
Gil.
Thank you.
Wonderful talking to you. All right,
Bye.
bye bye.